Dr. Habergham is not only doing postdoctoral research on all these matters, but is also very much responsible for science outreach, which we're all very keen on these days. So without more ado, I introduce our speaker today. Thank you.
Thank you. Thank you. Yeah, I'm showcasing a little bit the outreach side there. I think you probably heard, if you came last month, Mike Bode mentioned the National Schools Observatory, and it's our 10-year anniversary today, which also marks the amount of time I went to university 10 years ago, so it's a nice little coincidence for the both of us. So if anyone's interested in the outreach side, please feel free to speak to me afterwards, because that's what I'm project managing now. But I'm going to talk to you about what my PhD's been in and what my postdoctoral research has been in, which is looking at supernova explosions, specifically ones from very massive stars, and the fact that actually we don't understand, apart from the fact it's a massive star, what on earth exploded. So having a look at the environments in which those explosions occur to see if the local environment can tell us anything about the star that was there beforehand, and likewise, can the presence of these massive stars tell us anything about what's going on in that environment. So it works both ways. So the main collaborators I've had, Joe Anderson, who's now working out in Chile at ESO, Professor Phil James, who was my supervisor, and Joe Lyman, who was a PhD student after me, who's now working at the University of Warwick. I'll talk to you about what I mean by a supernova. There are many different types, so we've already gone into one of them in the intro. So what kind of supernovae I'm talking about, how they relate to star formation, and then the types of galaxies we see those supernovae go off in, and my particular experience has been looking at merging galaxies, so galaxies like the Antennae is a famous example, and other merging galaxy systems, or this one, you're probably aware, M82, Messier 82, which is a really famous starbursting galaxy where you've got the jets of gas moving out from the centre of the system. So I'll have a look at the merging systems, the starbursts that go on in those systems, and then draw some conclusions from there. So the supernovae I'm talking about today are specifically what we now call core collapse supernovae. They used to be called type 2. It's become more complicated, so now we call them core collapse because actually a few of the type 1 supernovae are core collapse as well. And these stars occur, these explosions occur when you have very, very massive stars, and the nuclear fuel that's been generated within the star that generates the outward pressure, which is always fighting against the gravitational pull. The star wants to collapse, but the pressure pushes out. The nuclear processes in the core is what causes that outward pressure. Now, eventually in these massive stars, the core fuses together elements so that you're left with iron. We can't fuse anything heavier than ions to still produce energy. So at that point, fusion's no longer an effective way to produce energy, to produce this outward pressure. So the fuel runs out. And at that point, the gravitational force wins out and the star starts to collapse inward. You get the outer layers of the star collapsing in. And when the outer layers of the star collapse in, you've got this very dense iron core still left at the centre. So they bounce off that iron core, and it's actually the bounce and the shock waves that blow the star apart. A lot of the energy is carried away in neutrinos as well, but it's that bounce off the dense core and the shock that comes out from that blows the star apart. And you're left with a supernova remnant, which can look very beautiful. You're probably all aware of this object, so Messier 1, the Crab Nebula. This is a supernova remnant from a star which exploded, I think it was in 1054. And we know this because it was actually documented by Chinese astronomers at the time. So Chinese astronomers saw this explosion happening, and now we can see the remnant of this as the Crab Nebula. So you're left with nothing of the original star, but what you are left with is in the centre either a neutron star or a black hole, depending on how massive the star was in the first place. And all of that material that used to be in the star is ejected and it's thrown out. And it's that material which helps to build the next series of stars that form. So it's a huge recycling process. And you often, this probably won't be the first time that any of you have heard the term that we're all made of stardust. Astronomers love to tell everyone that they're made of stardust. And this is why everything that's in yellow or blue on the periodic table here was produced originally in a very massive star, either during its lifetime, during the fusion processes, or during the explosion. Because during the explosion, the temperatures get so enormous that you can start to fuse heavier elements, heavier than iron. So the very first stars in the universe, we think, were all very massive stars. And because after the Big Bang, all we had was hydrogen and helium, a little bit of lithium, everything else that we have today was originally produced inside one of these massive stars. And it's the explosion which gets all of this material out and into the universe so it can be recycled into new stars, planets, and everything else that forms. So they're really important to try and understand. There's some other important things about them, apart from them distributing the matter into all of the surrounding universe. Some of these explosions, if you want the really, really picky classification, it's broadline type 1c explosions, are linked to gamma ray bursts. Now, I'm not going to talk about gamma ray bursts. It's not my expertise, and it would be probably a whole conference worth of talks to try and explain them. What we do know is that these are the biggest explosions that we observe in the universe, even more energetic than a supernova explosion. Apart from the fact that we see these huge explosions, we sometimes see a supernova associated with them. And that's essentially all we understand about these objects at the moment. There's a black box in the middle. Something happens, something explodes, and we see a gamma ray burst and sometimes a supernova associated with them. But because gamma ray bursts only last for a matter of hours, there's not much information we can gain from tracing that. It's very difficult to get a telescope focused on one of these objects quick enough to get any data from it. But the ones that come with associated supernovae, because the brightness of those can last for a matter of weeks, it means that we can try and understand a bit more about the gamma ray burst explosions as well. As I said before, they also lead to the formation of black holes. So this is the main process we get black hole formation in the universe, not the supermassive ones that sit inside the centres of galaxies, but your run-of-the-mill black hole. And they're enormously bright. And that's very, very helpful for astronomers because it means we can find them quite easily. And if you can find them quite easily, you can try and build up quite a big sample of them, and that's what we're looking at doing now. These are some examples of some nearby supernova explosions, and when I say enormously bright, you can see here this isn't a star in our own galaxy that's got in the way of this observation. This is a supernova that's actually associated with this galaxy. Supernova explosions within 2 weeks of the initial detection and explosion will give out the same amount of energy that our sun can produce in its entire life. So 9 billion years of the sun is equivalent to 2 weeks in one of these explosions. So that's how energetic they are, that's how bright they can be. If you see them outside the plane of the galaxy like this one is, it's very easy to spot them. Again, this one is sitting in quite a faint spiral arm, so it's very obvious when it occurs. But you do get some that sit perhaps in star formation regions in these clusters of stars and spiral arms, and it does make them a little bit more difficult to see. As an example, this is a supernova that went off in 2011, and you might be able to see at the top something getting brighter and brighter. This is a series of observations that were taken on the Liverpool telescope over a matter of 2 weeks. And this is how we find them still. This is generally how we find supernovae. We monitor galaxies, and you can take images night after night, and if something changes in that galaxy, something's happened, something transient has happened, something that changes with brightness over time. And this is an example of one of those supernova explosions. So there's nothing there initially, and then you can just see it getting brighter and brighter. And within 2, maybe 3 weeks, it will get below, it'll get to about the same brightness as the spiral arm again, so you won't see it unless you've got very, very deep observations. Here's an exercise for you guys. This is a more usual picture, so you're probably familiar with galaxies like this. Can anyone see the supernova explosion? See, you're all better than I am because it took me about 10 minutes to try and find this initially. So you can see just here, yeah, we've got a supernova explosion. So this is a kind of a before and after picture. Sometimes it is difficult to see these things, which is why most of the time now we have computer software do it for us. However, even now, the vast majority of supernova detections are done by amateur astronomers. Amateur astronomers will spend the time monitoring nearby galaxies night after night, and they're the ones who find out if anything's changed over time. So it's a huge contribution to this field, the amount of work that amateur astronomers put into this. This is an example from what we call now supernova factories. So this is one of the telescopes called the Paloma Transient Factory, which is out in America, and all it does is monitor a piece of sky night after night. And then, as I said, it runs it through computer software, and if there's something changes, it sends an alert, something's happened in this system, and then you have to try and figure out what it is that's happened. So this is it finding a supernova explosion over the course of 3 days, well, 3 nights. You can see how much brighter this object gets. So you can't even resolve the stars initially. Most of the galaxies that I look at are far enough away we can't resolve individual stars in them. So it's only really by seeing these explosions that you're even aware that high-mass stars exist in that part of the galaxy. So these are telling you something about the galaxy just by the sheer fact that they're going off there. But they can be difficult to find as well, which is why the software tends to run things more and more now. The factories and things like that, these supernova factories which have come into being in the past 5 to 10 years, have detected so many different transients that the importance becomes how to classify them. Not everything that changes in brightness in a quick period of time is going to be a supernova. It might be a nova explosion, it might be a gamma ray burst, it might be a variable star that no one knew about before. So you have to start classifying these objects. And supernovae initially were just classified by the presence or lack of hydrogen in their spectra. And initially, all we said was, okay, if there is no hydrogen present in the spectra, we'll call it a type 1. And if there is hydrogen in the spectra, we'll call it a type 2. And even up until the 70s, this was as far as supernova classification went. When the statistics started to improve, the technology started to improve, you could see more detail in the spectra. We actually realised that type 1 were not a single object. There's three simple types of type 1 classification. There's A, B, and C. The theme of this talk is going to be that astronomers are not creative. So we have these 3 different types. And these type 1As, you're probably all aware of. It was Nobel Prize winning physics, I think back in 2011, because these are the ones that have been used to figure out the expansion of the universe, the acceleration of the universe. Because these are not core collapse supernovae. These supernovae do not come from massive stars. They're completely unrelated to everything else that's this side. These supernovae, again, it would be about 12 talks. We still don't completely understand them, but what we do know is it's from a low mass star. It's not from a high mass star. It's from a low mass evolved star. So it's towards the end of its lifetime. Something like the sun will end up as a white dwarf star eventually. And that's what these objects come from, a white dwarf star, but they're in a binary system with something else going around it. And there's what we call, well, binary mass transfer, so the less evolved, the more massive star starts pouring material onto the surface of the white dwarf. And eventually the white dwarf can't take that much mass and it explodes. It reaches a limit, it's called the Chandrasekhar limit. Because these stars always explode at about the same mass, they're roughly the same brightness. Because they're the same brightness, we call them standard candles, or now they're called standardizable candles because they're not exactly the same, but we know how to tweak it to make them the same. And because these things are standard candles, it means that you can figure out distances to objects because you know how bright it should be if it's at a particular distance. So if you're seeing one somewhere else, you can figure out how far away that is. And that's how the Nobel Prize for Physics was won, by seeing these explosions in distant galaxies and actually working out that the ones quite far away were not just, the universe wasn't just expanding, it was accelerating as it was doing so. But these are nothing to do with core collapse stars, they're nothing to do with massive stars, they're completely unrelated. Everything this side is a core collapse supernova, so they're the ones that I've been concentrating on. It can get more complicated because there are types that seem to be in between these that we can't quite decide if it's a B or a C. The type 2s now are also divided into at least 4 different classes. 2n is an example of those. There's also 2p, which means it has a plateau in the light curve. There's a 2l, so it has a linear declining light curve. And there's a 2b, because that's somewhere in between a type 1 and 1b and a type 2. So this isn't as simple as this makes it look, but for simplicity, we'll split it into type 2s and 1bcs. The 1bs, even though they're lacking hydrogen, do show helium in the spectra, whereas the type 1cs have lost both hydrogen and helium before the explosion. So that's how we differentiate between those. In order to help the statistics, rather than dividing into all these tiny little groups, people tend to classify them. We'll group the type 2s together and the 1bcs together. So for much of my talk, I'll do the same thing. So if these are massive stars, we expect them to occur in regions of star formation, because massive stars burn through the fuel much more quickly than low mass stars. So they don't get a chance to migrate away from where they were born. They've got very, very short lifetimes, and in astronomy, when we say very short, we mean anything between 10 and 100 million years. But that means that we find them near star formation regions. And if it was in our own galaxy, that's fine, because we can physically see the star formation regions. This is an image from Hubble of a star formation region in our galaxy. You can see the dust and the gas where these stars are forming. Behind you can see the blue light. That's from a star that's a protostar, which is exciting the gas behind it. So if it's in our own galaxy, we can see these things. Another famous example, the Orion Nebula, which is just underneath Orion's belt by his sword. So we can see these regions in the Milky Way. We can resolve the stars, we can resolve the star formation regions. So if we could find supernovae in them, or near them, that would be fantastic. Except that supernovae are very, very rare. For every star like our sun, compared to every star like that's going to eventually turn into a supernova, you need 100 stars like our sun to produce one of these. So they're not common things, they're not common objects. In fact, we wouldn't want one going off too close to us because they're hugely energetic as well. But we don't see them in our galaxy very often. There's a chance they've gone off the other side of the galaxy and they've been obscured by all of the dust between us. But we're well overdue seeing one in our galaxy. So we have to look outside. We have to try and build up samples outside of our own galaxy. So we want to look for these star formation regions, but how do we see them when it's not in our own system? And what we do is we look for this line here, which is the H-alpha line. That occurs when we've got gas and dust. We've got something very hot near the gas and dust, so a forming star. That very hot object excites the gas and the dust. So the hydrogen jumps up an energy level. Eventually it runs out of energy and it drops back down again. And when you get that drop, we see this H-alpha line. It's a very specific line. It occurs where we've got these star formation regions, so it's a fantastic tracer of star formation in other galaxies. So you can either take a spectrum like this of different galaxies, or what we can do, and what I've been utilising, is put a narrow filter over this H-alpha line. So you're just picking up the light that falls in that small part of the spectrum. And what we can do then is, if we've got that image and we've got an image of all of the light, we can get rid of this continuum, the stuff that just comes from the galaxy as a whole, and it'll just leave us with this star formation. So a few examples of this. This is one of my galaxies. We have a database of about 700 galaxies, nearby galaxies, so we're thinking within about 60 megaparsecs, something like that, from the Milky Way. This is the object in an R-band observation, so we're looking at the red light, the background stars. A lot of the old stars appear bright in this image. Now if we look in the H-alpha, this is what we see. So we can just look at the regions where we've got this excited gas. We've got excited gas, which usually it's a bit of a mystery in the centre, because you might also have something in the centre of the system like a supermassive black hole, which might be exciting gas, but certainly in the spiral arms, all these little blobs that we've got, they're regions of star formation. So we can trace this star formation in other galaxies. It's got a really good purpose as well. If you have a look at this system, this is a merging galaxy system, but you can see we've got quite a few galaxies in this image. Now if we just look in the H-alpha, all of these other galaxies disappear. And that's because they're at a different redshift, they're at a different distance from the Milky Way. So because we're looking at a very, very thin part of the spectrum, a very narrow range in wavelength, anything that's further away has been redshifted out of that filter. So it moves out so we can get rid of any background systems and we can just look at the one system that we're interested in. And this merging system's got a huge amount of star formation in the cores of the galaxies, but we're getting rid of all of this other stuff. So we've done this. We've got, as I said, observations of about 700 galaxies. They've not all got supernova in them. We've got about 400 that have supernova in them. And they were almost exclusively taken by these telescopes out on La Palma. This one, unfortunately, is not being used anymore. It's the JKT. I can never pronounce it, so I'm not going to try. So the JKT telescope was part of the Isaac Newton group, which the UK has got a stake in. But it's a small mirror and they decided to close it down, so unfortunately it's just sitting on the island, not being used now. There's also the Isaac Newton telescope, which is just over a 2-metre mirror, and this one, which if anyone came last month you'll have heard all about, which is the Liverpool telescope. Obviously I'm quite biased because I work in Liverpool, but this is our baby. This is our robotic telescope, 2-metre, biggest robotic telescope in the world. And it's very useful for looking at things like supernova explosions because it can move so quickly towards them. A normal telescope like this, you have to wait for the dome to rotate before you can point the telescope out of it. Usually the telescope gets there and you're still waiting for the dome to trudge around to catch up with it. Because this one doesn't have a dome, it has a clamshell and the whole thing is exposed to the night sky, it can move around the sky very, very quickly. So this thing can actually directly receive a text message from a satellite which is trying to find these things called gamma ray bursts, and within 1 minute it can have stopped whatever it's doing and start looking at this explosion. So that's the benefit of having robotic telescopes with no people involved. This is an example of the Liverpool telescope moving throughout the night. So as well as the main telescope, it has 3 cameras attached to it. I won't go into details, but this is the one that's attached to the enclosure. So it actually gets an observation of what the telescope's doing all night. And you can see the time going across the top, but every time it moves, you can see how quickly it's moving between objects. The moon's about to come up and spoil everything now. The moon's very pesky. Yeah. But it's fantastic that it can move so quickly. It can get onto these objects really fast. So that's another one where we've got observations from. So if we want to see if this is true, if they are from massive stars, and we've got these H-alpha images, do the supernovae trace the star formation? That's the first question. And these are some examples. So again, this is the H-alpha image. So everything you're seeing here is where you've got excited gas. And this is a type 2 supernova. It's quite close to what we call a H2 or a H-alpha region. But this is another type 2 from a very massive star, and it's all the way over here. This is a type 1bc, and it's sitting bang in the middle of this galaxy in this huge area of star formation. So we've essentially done this for all of our sample of 400 and odd galaxies, and actually what they found is that the type 2 supernovae are not necessarily associated with the H2 regions, with this H-alpha line, but the 1bc's seem to always occur in regions where we've got star formations still going on. So we think that this means they have a higher mass than the type 2s. Because as I was saying, the more massive the star, the more quickly it runs out of fuel. So it has a shorter lifetime. So the ones that are not associated with this current star formation, perhaps they're less massive, they've had time to move away from these star formation regions, or the star formation region in which they were born no longer exists, it's run out of fuel. So we think that there's a mass sequence, actually, if we split this down, going from type 2s to 1b's to 1c's. And that seems to make sense because if you remember, the type 1s have lost the hydrogen. So what we're thinking is that the star prior to explosion no longer has a hydrogen envelope around it, it's lost this hydrogen envelope. The 1c's have not only lost the hydrogen, they've lost the helium as well. So something has got rid of that envelope before the star's exploded. And one of the most likely reasons for that is that it's a very, very massive star with very strong stellar winds. And the stellar winds can literally, in stars this massive, blow off the outer envelopes prior to explosion. So perhaps we have got a mass sequence between these types. We've certainly got what people are calling now an envelope stripping sequence, but it's what causes that envelope stripping that's a bit controversial. For the sake of our work, we've assumed that it's a mass sequence. That's the most simple explanation for what we're seeing. So if we've seen that these things possibly have a mass sequence in them, we can have a look at the kind of galaxies they go off in. These, obviously, you know, the two main types of galaxies we have in our universe. We've obviously got dwarf galaxies. We do sometimes see supernovae in these dwarf systems, but not very frequently. What we do find, looking at these different types of host galaxies, is that core collapse supernovae, the ones from very massive stars, only occur in spiral systems. We don't see them in elliptical galaxies. The type 1As, which were used for cosmology, we see those in both. And we expect that because these massive stars are young stars. They're coming from regions of star formation. We don't have active, certainly don't have very much active star formation in elliptical galaxies. So we do expect them to come from spirals. But what do the spiral galaxies in our sample really look like? It would be lovely if they were all like this. A beautiful face-on spiral galaxy. You can resolve star clusters. The bright objects are clusters, not individual stars. Each one of those clusters might contain 10,000 or more stars. But if you can see it face-on and a supernova occurs, you can literally see that whereabouts in that galaxy it's gone off. Of course, we also get galaxies like this. And if we see the system edge on, these supernovae are so bright they can shine through a lot of the dust. So if we see a supernova that occurs here, we don't actually know on the plane of the galaxy where that supernova's gone off in. So we have to be very careful when we're looking at the sample what we can get good information from and what's essentially, unfortunately, going to be useless. So everything in our sample that's edge on for us is useless in trying to find out some detail about the particular environment the supernova occurred. And when we were looking through, we saw a lot of these kind of systems. I call these train wrecks. But this is where we've had systems merged together. So you're aware everything in space is not stationary. Everything in space is moving. Now, on the large scale, everything's moving away from each other. But on the small scale, things can move towards each other. They've got huge gravitational pulls towards each other, and we can get huge mergers like this. You can get clusters of galaxies together. It's the Virgo cluster. So you've got, well, in the whole Virgo cluster, you've got hundreds of galaxies if you count all the dwarf ones as well. So mergers are quite common when we're looking at galaxies. This is a really nice example. And what you see is that they're obviously disturbed. When you see optical images of these systems, you can tell that something has happened to it. You would not look at this and think that that galaxy had formed that way. Something has happened to it. So we've got a trail from a galaxy which probably fallen into the centre of this one here. So disturbed systems or merging systems do look very different on optical images. You can tell that there's something happening between them. Sometimes you see the two galaxies as separate entities. At this point, this is one galaxy nucleus which has fallen to another one. So you get them in all different stages of collisions, but you can tell from the optical images, just by looking at the optical images, that they are disturbed. The reason I think it's quite interesting is because this is a simulation of our galaxy, the Milky Way, and the Andromeda galaxy, because we are moving towards each other. And on about the same timescale that the sun will cease to exist, so in about 4 to 5 billion years' time, we're also going to start interacting with the Andromeda galaxy. So in 5 billion years' time, we will be in one of these systems, these merging systems. Now, there's still a lot of debate about even how galaxies formed and evolved. We still don't know the answers to those questions. But one thought is that the elliptical galaxies we see today are the result of these spiral galaxies merging together. So it can change the galaxy. So if we've got supernovae in these systems, it can tell us something about the galaxy as well, because you know you've got this very massive star, these star formation regions occurring. So what we do is we try and look at whereabouts in the galaxy these explosions occur. And we do something that's just a radial analysis. So what we do is we take an ellipse which reflects the size and shape of the galaxy, and we take it to where you're including all of the light that comes from the galaxy. So as soon as you start hitting the levels that you get in the background sky, you know you've encompassed all of the light from the system. And then we shrink the ellipse down until it just encompasses where the supernova's exploded. And it gives you, if you take this as a fraction of this, it gives you a value between 0 and 1, and that's some sort of radial distribution for the supernovae. So if it occurs right in the centre of the galaxy, it'll have a value of 0. If it occurs in this outer ellipse or outside of it, it will have a value of 1. So you know whereabouts in this system the supernova's gone off. And doing it this way means we can compare different galaxies. Because if we just did this as a distance to the centre, you might have a galaxy which is 4 times as massive as another galaxy. Now, if you've got the same distance from the centre, in the very, very massive galaxy, that might still be within the nucleus, but in the small galaxy, that might be out in the spiral arms. So if you do it this way, and you get a value between 0 and 1, you can compare lots of different galaxies. So we did this for all of our sample, and we split the galaxies into things that looked disturbed, things that looked like they'd been in collisions or mergers, and things that looked normal, like a normal spiral galaxy without any interaction. And we did the classification of disturbance by eye. It's still the best way to do it. Humans are fantastic at picking up patterns, and we can see these things often with a lot more precision than a computer program can currently do. So there are people working on shoving huge amounts of galaxies through computer software, and the software will tell you which is disturbed and which isn't. It doesn't usually give you as accurate or as good a result as actually visually inspecting all of the systems. And there are a lot of really easy telltale signs that something's been disturbed. So you might get tidal tails like we have in this system here and here. You can get double nuclei, so where you've seen the remnants of what was 2 individual galaxies. You can see ongoing interactions where you can physically see the 2 galaxies there. And strong asymmetry as well. If it's very different on one side to the other, usually something's happened. So we classify all the galaxies as either disturbed or undisturbed. And then we had a look at where these supernovae were going off. And in the undisturbed galaxies, it's fairly flat. There's a bit of a dip in the centre of towards the centre of the galaxy's light, where we're not seeing as many supernovae. In the disturbed ones, it's a little more peaked towards the centre, but when we're looking at all of them together, you can't see very much difference. But if we split them by the different types and we look at the type 2s and the 1bc's, there's a huge difference in where these supernovae are going off in the galaxies. So within these galaxies which are merging with each other, we get a huge peak of the 1bc's, what we think are the most massive stars, in the centre, and the type 2s, the less massive supernova, are going off in the more outer regions. The probability that this difference occurs by chance is 0.4%, 0.4%. So something is different between these 2 different types. Something's happening here. We think that type 2 supernovae come from stars which are between 8 and 16 times the mass of the Sun. The type 1bc is anything more massive than that. So you're thinking about 16 times the mass of the Sun to anything up to 200 times the mass of the Sun. So if you remember what I said before, the universe prefers to make smaller objects, 100 suns for every 1 star that will turn into a supernova. So it's preferentially we're seeing the most massive stars in the centre of these systems, which goes against what we think star formation is. We always think it's easier to form the smaller stars, so we expect to see less of these stars and more of these ones. This is a few samples of some of the different disturbed systems. Some of them you can see have got really peculiar dust lanes and things. Now what we said was, unless it's 2 systems where we can physically see them interacting, it had to show 2 other signs of disturbance before we classified it as disturbed, because sometimes a galaxy can just be a little asymmetric, but actually have not had any kind of disturbance. So we had a fairly robust way of classifying these things. So what we're seeing is that there's an excess of core-collapsed supernovae, so an excess of very massive stars in the centre of disturbed galaxies, but it's also dominated by type 1bc. So what we thought we'd have a look at, there's one particular galaxy in our sample, which is my favourite, called ARP 299, or NGC 3690. And it's been called a supernova factory because, as I said, these things are really rare. In our galaxy, we expect one to go off about once every 100 to 200 years. In ARP 299, which looks like this, a hugely disturbed system where you've got two massive galaxies interacting with each other. These are the number of supernovae that have gone off in it since 1990. So we expect in our galaxy 1 every 100, 200 years. This system has had 1, 2, 3, 4, 5, 6, 7 since 1990. So it's producing a huge number of supernova explosions. So we had to look at this one particular system, and unfortunately, because still in the early 90s, the technology wasn't good enough to classify these objects well. There's a few that we don't have classifications for, but you see that there's some 1Bs, one that's somewhere in between, and there is some sort of inclination that perhaps these 1Bs are occurring more centrally, even in this one system, than the type 2s as well. So the idea is, well, why are we getting central star formation in these systems? And actually, that one turns out to be fairly easy to answer. Now, when my PhD supervisor was doing his PhD in the 80s at Imperial, down here, he actually looked at infrared imaging of galaxies. Because there was something that was new at the time. There was things called infrared galaxies or infrared bright galaxies. And they'd only just been discovered. And the idea was, well, why are these bright in the infrared? And this is some examples of them in the infrared. You can see these huge spikes of light towards the centre. Why are these things so bright in the infrared? What's causing them to be bright? And actually, when you look at these objects in the optical, this is what they look like. So these are highly disturbed galaxies. So we've seen these spikes of infrared emission, usually towards the centre, in these disturbed systems. There's been a lot of theoretical work into why that is. Why is it all centralised? And what we think is that when two galaxies merge, the gas and the dust that was originally distributed throughout the entire system funnels into the centre of the two. It follows the centre of gravity. So you get all of the gas and dust ploughing towards the centre of the system. So you get this huge build-up of material that can produce stars. You need gas and dust to be able to produce stars. So if you funnel it all in to one small region, you increase the density, you increase the likelihood of forming stars there. So we would, in these merging systems, expect to see lots of star formation in the centres. So we can understand that. We can understand why we're seeing supernovae go off in those regions. So the interacting ones, the merging systems, have strong bursts of central star formation, and it uses up most of the gas that was originally distributed throughout the entire system. So we thought, well, let's have a look using this. This is a Spitzer Space Telescope, which looked in the infrared. Let's see if any of our galaxies are in the archive of this telescope, and we can actually see if any of them are showing signs that they've got starbursts going on. And this is our example in R band. This is what it looks like in H alpha. You see in Spitzer, the one galaxy of these two where the supernova occurs, which is this white circle here, has got a huge burst of star formation. You can see it in the infrared. Interestingly though, the other galaxy in this system's not got anywhere near as much star formation going on. This is another one where actually in the optical you might not think it looks too disturbed, but we've got a very unusual dust lane here. And when we look at the H alpha, you can see that that's where we see a lot of the star formation occurring, and it's the same in Spitzer. So we are seeing that these things are going off in galaxies that are showing signs of these huge bursts of star formation. So that becomes obvious. We can explain why we're seeing them centralised in disturbed systems. But why we're seeing them dominated by the 1bc, the stars that we think are more massive prior to explosion. And it's much, much harder to answer that. I've said a few times, and you've probably just taken it as I've said it, that we know that hundreds of stars the size of the sun are formed for every one that will explode as a supernova. Now, the reason we know this is something called the initial mass function, which is a very fancy way of basically counting stars. So what we've done in our own galaxy in the solar neighbourhood is we've counted the number of stars in different mass ranges. So how many stars do we see that are the same mass as the sun? How many stars do we see that are a tenth the mass of the sun, or 100 times the mass of the sun? And we count them all up, and it gives us a mathematical function that tells us how many stars we expect to see formed at different masses in any particular star formation region. And in our galaxy, which is the only place we can do this properly, because we can resolve the stars properly, every one star that will go on to produce supernova, we get hundreds of low-mass stars. There's a chance that with bigger and bigger telescopes, we'll be able to do this in other galaxies. We can just about do it in the small and large Magellanic Clouds, the nearby dwarf galaxies. But we've assumed, as astronomers, that this is universal. It happens in our solar neighbourhood and it happens everywhere else in the universe. If this is universal, then what we're seeing in the centres of these merging systems doesn't make sense, because we're seeing more of the most massive stars. There are some predictions that perhaps in different environments this might change, but it's very controversial if you say this to a lot of astronomers. And this is one of the theories behind why it could change. And it's basically that the shape of this IMF, this initial mass function, doesn't change in the environment, but actually the peak mass might. Because in these regions where you've got very dense star formation, you've got very high temperatures. And the temperature is what dictates when a cloud can fragment and form stars. In very high temperatures, the fragmentation occurs at much higher masses. It's called the Jeans mass. So perhaps that's what we're seeing here, in that we've got these high temperatures, which is shifting the peak of this initial mass function to something in a starburst region which is peaking around 10 solar masses, which is the kind of size of star that we'd expect to see go supernova. So there's a chance that this is what we're seeing, and this would be the first evidence to suggest that this is the case. But as I said, it is controversial. So there's a chance that if this is a progenitor sequence, which most people seem to agree is a mass sequence, then what we're seeing is evidence in the centres, just in the centres of these merging galaxies, that the star formation there looks nothing like the star formation we see elsewhere in the universe. If it's correct, it's controversial, it's new, it's something that I can see it happening. And why would you expect the star formation in a normal star formation region in the spiral galaxy to look anything like in the very energetic, very dense, very hot regions of these merging systems? But it's not accepted widely. In the most extreme case, when you get these mergers, if it is true that these mergers produce ellipticals, which again is currently an unknown, you can see how it would work, because you've got young stars in these spiral systems, you've got a lot of gas and a lot of dust, and we don't see that in the ellipticals. But if we get these huge bursts of star formation that use up all of the gas and dust, then actually what you can do is get rid of all the gas and dust, get rid of any potential star formation in very massive stars which will explode and leave no remnant. So you're not going to build up the stellar mass. It will have more things like black holes in it, but we're not big enough that we can detect. So this might be a way that we can provide evidence for what we call the hierarchical merging of galaxies, small galaxies merging together to form more massive ones. And one of the reasons it's so interesting is that we're looking at very, very extreme environments, but these are the environments that would have existed in the very early universe. If you look at optical images, for instance, from the Hubble Deep Field, and you're looking back to very high redshift, looking at some of the first galaxies that ever formed, they don't look like nice spiral normal galaxies. They look very, very disturbed. There's a lot of interaction happening. And we know that the first stars were very massive stars. So by probing these very extreme environments, it's actually given us some sort of indication about the environments that existed in the very early universe as well. So there's a lot we can learn going both ways, by looking at the environments to tell us something about the supernova explosions, but also using the presence of these supernova explosions to tell us something about the galaxies in which they form. So I will leave it there and open for questions.
Well, thank you very much. There's a roving microphone around, so we'll invite some questions now. Gosh, that was a stunning one. They're all stunning. Now, wait a minute. Let's try over here. Now, I'll get this section of the audience to think quickly.
I've got.
There we are.
Yeah,
there's one there.
Embarrassingly simple question, I'm afraid.
Yes.
How do you distinguish, I've always wondered about this, between a nova and a supernova?
It's mainly in the brightness. So supernova explosions are much brighter than novae explosions. The other thing with novae is that they're outbursts, but the star survives the explosion. So usually if you wait for the peak of the eruption to finish, you'll still see the star there. Supernova explosions are fatal. They completely get rid of the star, so you don't see anything afterwards either.
Isn't it true to say that a nova is repeatable?
Yes, we think all novae are what we call currently novae are classified as either classical or recurrent. Recurrent means that we've seen them go off more than once. Actually, the thinking at the moment is that everything is recurrent. It's just the timescale that changes.
We haven't been here long enough.
Yes, exactly, yeah. And we think that they might be the progenitors, the precursors for type 1a supernova explosions.
Yeah, here in front.
How close to our own solar system would it have to be a supernova to wipe us all out?
Well, I'm not sure exactly.
Could you repeat the question because it's being recorded? Yeah.
I said, how close to our own solar system would a supernova have to be to wipe us all out?
Yeah, it's a difficult question to answer. Now, luckily, the stars in our solar neighbourhood are very much like the sun. So none of them are big enough that they'd ever explode as a supernova. But these things are hugely energetic. If anyone works in ergs, it's 10 to the 52 ergs. Now, what that means, if you try and picture it, is the collisions that are happening at CERN to supposedly found the presence for the Higgs boson. That's the most energetic thing we can do here on Earth. Now, you'd have to times that by 10 with 22 zeros after it to get up to the explosions in these objects, the energies in these objects. They're hugely energetic. So exactly how close one would have to be to disrupt us here on Earth, I'm not sure. But they throw out very high energy particles, which is what's dangerous. It's like having solar radiation, just the particles we get from the sun every day, but timesing that by millions of to get the same effect. Now, one went off in the Large Magellanic Cloud in 1987, SN 1987A, and we detected some of the neutrinos from that explosion here on Earth. And everyone's probably aware, neutrinos are very, very low mass. At one point we thought they had no mass, so if they've no mass, there's nothing, you can't interact with anything. So it was actually the detection of those neutrinos that proved the existence that they had some mass, the fact that we detected any at all. But these things will produce billions of neutrinos, and we detected 2. It's the ones that you don't detect that pass through everything that you need to be worried about. So that was in the Magellanic Cloud, but it didn't cause us any damage here on Earth, apart from a few satellites and things like that, because you can get the interaction of the particles with the satellites. In our own galaxy, it would be nice to have one because we'd get a huge amount of information from it, but it does need to be far enough away that it wouldn't damage us as well.
Yes, can we try over that side? Distributing the questions a bit.
I was going to ask, what would be like the causes and like the effects on the surroundings if a gamma ray burst were to happen?
A gamma ray burst would be more damaging than a supernova because it's probably 10 to 100 times more energetic than a supernova. So you get the same and we call them gamma ray bursts because the particles we detect from them are in the gamma ray part of the spectrum, which is very, very high energy part of the spectrum. So if one of those, it would be the same thing. If one went off too close to us, that would be even more damaging than a supernova. But we've not detected any of those nearby.
Thank you.
There's one over here. The lady there.
Thank you. This is a naive question, but I want to know how these photos are taken and the different colours that they show. I mean, is there a process that brings out these colours?
With the ones that I've particularly used when I was talking about the H-alpha and things, so we put different filters on the cameras that we've got attached to the telescopes, and those filters will only look at particular wavelength of light. So we have broad filters, which some of the what I've called continuum images are taken with. All right, that will do actually. So this one, for instance, is an R-band image. It's a broad band, but it's looking particularly at the red light that comes from the galaxy. So we can put these broadband filters over the cameras and just get particular wavelengths of light. So what you do with these ones is you put a very narrow filter on, so you're looking at a tiny wavelength range. So only light which gets emitted in that wavelength range will show up in your photo. But it means you can tailor where you put that small wavelength range to capture different things. So here we put it over the H-alpha line, so we can just see where star formation is taking place. But at the same time, if you're looking for active nuclei to galaxies, so things like supermassive black holes interacting with things around, you can put a narrow filter on that will just look in a particular wavelength range to look for the signs that something like that is happening as well. And then what we do is, the image doesn't appear like this to start with. What you have to do is take away the light, because you still get the background in this. So you take away the light from this, from the original, and then you just pull out the star formation regions. Okay.
Well, at the back over there. Yeah.
What type of supernovae do you think produced us?
Produced us. The kind of supernova that existed in the very early universe were probably unlike anything we see now, because the stars that existed in the very early universe are nothing like what we see now. We call them population 3 stars. We've done it backwards for some reason. We have population 1, 2, and 3. And the very first stars that existed in the universe would have been purely made of hydrogen and helium. That was the only elements that were around initially. So those stars, we think, would have been much more massive than the stars we see today. I mean, we've detected stars in the current universe that are up to 250 times more massive than the Sun. We think these population 3 ones were even more massive than that. Very, very massive stars, and made purely of this hydrogen and helium.
So when would that have been? I mean, we're 5 billion years old, almost.
Yeah.
The universe is almost 14 billion. What time in between did this happen?
A cosmologist would know better than me. I can't remember the exact timescales. After the period what we call of reionization, which is when we can start to see the universe. So this is going back as far as we can see to the cosmic microwave background. Now there's a period after we see the cosmic microwave background where we can start to see the formation of galaxies and stars. Well, galaxies. We can't currently see the formation of those first stars. We don't have the capability of doing that. So it's sometime between what we're seeing in the cosmic microwave background and what we see in the very earliest galaxies. That's when you get in the formation of the first stars. I can't put a time on that, but I'll be able to find out.
Thank you.
Yeah, this is actually a question that relates to the last one somewhat. When you put up your slide on the elements of the periodic table showing that some of them came from supernovae and others came from large stars, it triggered a recollection in my mind that I've always been puzzled about the elemental composition of the Earth and presumably Mars and the asteroid belt and maybe Venus and Mercury. We have a fairly substantial amount of elements that are higher up in the periodic table that make up the crust of the Earth and so on. Can you, and yet when a supernova explodes, it dilutes its 10 solar masses into an enormous volume. And it intuitively never seems to make sense to me that there could have been enough supernovae or other, large star formation of these elements to create the dust that would, condense into the Earth and have the heavy elements that we have. Has anybody tried to do a backwards calculation to figure out if there had been enough supernovae to explain what we have today?
Whether it's been done locally to look at the exact composition of what we have on Earth, I'm not sure. That's an area that geologists would know a lot more about than I would. But there are a lot of models, and the thing is, it's all computer models, it's all simulations, to try and look at what we see globally in the universe and where that has come from. And that's how we come to understand things like the first stars must have been massive stars, to get the production so early on of these heavy elements, knowing what we started with and knowing what we've got now, to get all of these heavy elements, the very first stars must have been very massive and must have exploded as supernovae. It must have fused together these heavy elements that we see today. Locally, about the composition of the Earth and what the solar system is made from, I'm not sure. The problem is with everything that there's very little observational evidence for anything. We rely on computer models. And as I said a few times about my work being controversial because it changes what we think of as the initial mass function being universal. One of the reasons it's controversial is because modelers put that in as a fixed law that can never change. Yeah. So if you provide evidence that might change that, it can change the models as well. So.
Thanks very much. What exactly is the mechanism thought to be for making these heavy nuclei? Because you would have thought that in an explosion, everything is flying apart.
It is
it's not enough to say it's very hot and the pressure locally is high or whatever, because everything in an explosion really is flying apart.
Yes,
is it to do with the bounce?
It's also crashing into each other. So you're propelling things into each other, and because the temperatures are high enough that you can get over the binding energy of iron, you can fuse heavier elements, and everything does eventually fly apart, but you're talking about very small timescales. A lot of these things will literally form in the matter of seconds or fractions of seconds because of the huge energy, the huge temperatures, and the fact that everything's crashing into each other. So when things bounce off the core, it doesn't happen simultaneously. You get the different layers of the star collapsing at different times. So when you get the first thing bounce off the core, it crashes into the next thing that's coming towards the core. So there's a lot of crashes, a lot of shock waves, and a lot of energy in those.
So you're saying that iron is the cause of the trouble then, isn't it?
Yeah.
So the next question is, what made the iron? But we won't go into that one.
Yeah.
Thanks for a great lecture. I'm just a layman, so please forgive me. As I understand it, this is all generated by nuclear fusion,
yes,
as opposed to what we do on Earth, which is nuclear fission.
Yeah.
With regard to Isaac Asimov and the idea that science fiction becomes tomorrow's science fact, do you think there's any chance of our generating energy in a similar way for an energy-hungry 7 billion
There's currently a lot of work. There's currently a huge amount of work going on to try and produce fusion here. So there's the JET facility, which is down in Oxford, the Joint European Torus, and that's the main place that's leading it in the UK. But they're about to build a huge prototype fusion station in France as well. And there's a lot of work going on to try and... Because if we can crack fusion, we can crack the energy crisis. It's just at the moment, we can't get it to produce enough energy. So we have to put more energy in to getting the temperatures and everything else high enough to actually get any energy out.
Thank you very much.
Can I just ask a quick...
Would the centre of our galaxy originally have been a starburst environment? If so, why isn't it now?
It's an interesting question because we still don't know how galaxies formed. If we adopt the hierarchical merging model, which is that lots of small things join together to produce bigger things, then spiral galaxies must have formed from smaller objects merging together. It's still up for debate whether that's the case. Actually, we don't know if it was hierarchical or not. So if there was that, if there was the merging, then there is the chance that there would have been supernova go off because you'd have the same process just on a smaller scale. But our galaxy as it is, as a spiral system, shows no signs of any major interaction with another galaxy. So we know there are some dwarf galaxies which we think have actually passed through the Milky Way before, but they're so small that they don't have a very big gravitational effect on the Milky Way. And you need to have systems which are quite close in mass to get the gravitational interaction which causes all of the material to kind of fall into the centre of mass.
So you need to have that interaction.
Yeah, for this process to happen, you need the interaction. Yeah.
Okay, there's one over here. We'll take that one first, then over here.
Hi. All the elements, were they initially produced from the very first supernova explosions, or was there like a few generations and they were built up?
So it's like I'm not sure on the exact answer. It's likely that there's a few generations to get where we are now. But you have, it's not just during the supernova explosion that you're actually fusing elements, because the stars are fusing them all the time during the life as well. So you'll see some of the things in red on here are produced in small stars like our sun all the time. Yeah. Well, small stars can't get as high as iron. Large stars can. So you get the fusion going on constantly during the star's lifetime, building up some of the elements, and then it's during the supernova explosion you can build heavier ones. You would probably need a couple of generations to produce everything that we've got now, just because the timescales are so short to actually have that fusion process during the explosion. But certainly a lot of them would have been produced in the very, very first stars.
Thank you.
Thanks very much for this lecture. I was intrigued when you said that the modelers produce their models looking at our galaxy. Mm. And then you looked at some other galaxies and you got data. And from that data you said these different things would happen. And the modelers, instead of saying that's very interesting, are you saying they said, no, you're wrong?
I'm not saying that
Are they hung up on their models, irrespective of the data that you're putting in front of them?
I'm not saying that every modeler will say this, but I went to my very first conference, my first year of the PhD, as a 21-year-old, and gave this talk in front of a group of very eminent astronomers and was told that my data was wrong. Yeah, which is why it turned into a whole PhD's worth trying to explore every possible explanation and to see if the trend still existed when we increased the statistics, and it's still there. We've increased the statistics year on year and it's still there.
And you're still getting opposition?
Yes. Yeah.
That's very interesting.
Yeah.
Right, I think we're going to have to bring this to a close now. We've gone past the magic hour of 2 o'clock. So, Wednesday, give a big hand. Thank you very much.